Okay, so how many people actually check out the pre-lecture for this? Yeah, it's on syllabus, but don't worry because the earlier half of this lecture is pre-lecture material. We're going over it again, but I'm curious in case you guys go over that, I'll go quickly because there's a lot of things we have to cover. All right. Otherwise, I'll go whatever rate we have to go right now. Quick brief. Oops. Uh, we from Tuesday, right? We treat connection as you want to connect file, right? Again, every single IO is a file. So if we want to actually establish two connection, one thing we can do is like, okay, you have data streaming in and out, right? From one server to another. We can think of it as I stream into the file, and then this guy would read out of the file and somehow make sure there's a connection to say, hey, go there. All right. Now here's the internet at a glance. Ideally, what we want to do is to be able to make sure that so first of all, every server can see the client. Every server can see its, like whatever data that it has to access from another server. Every client can access the internet and go to the server and get some reply. If you want to go to Google, they should give you this search prompt, which you can then type something in, which would kick in the Google server to search, for example, the database server for that particular keyword search. Another server from compute on, okay, what do you exactly want? It doesn't like flat out just use the phrase, right? It tries to do some like machine learning to actually make sure maybe it is what you want. So it try to rank what page should be ranked first, what page should be ranked next, right? I mean, that's why we use Google, because they're doing really good job at making sure that maybe the first 5 links is what you are searching for. Not like you don't have to go like 10 pages and find where you're looking for, right? So the logical structure, sorry about animation, but wherever you want, forget about the circle, it's supposed to come up later. Let's say you have 2 hosts. Let's say you have 2 hosts, all right? I want to connect them. The high level, or the high level way we can look at this, it's like a bridge. That I can send the data back and forth and back and forth and back and forth, right? These data can be command, do this. Raw data, these are the image. These are the text that you're searching for. How do we link them, right? So first of all, if you if you ever have to configure the internet, say at your house, right? The first thing you have to do, buy a router. What does a router do? Why do I need a router? Well, for your home kit to connect to the ISP, right? You basically have this machine sitting in the middle that tells you, okay, if I want to go to say Google, send this packet to the ISP, which hopefully that have some connection to the host, right? Look at it that way, right? Now let's assume something a little bit more simple, right? You have a like MUIC internet. You don't have to go through the ISP. Everything is connected. In this case, one circle of host and router can connect to another circle and they can talk to each other, right? Quick question. I mean, if you want to connect one host to another, do I really need a router? Can I just connect the internet cable from one to another? Yeah, you can do that too, right? So why do I need a router? Obviously, first of all, right? Well, yes and no. So if you use router as a connection, there has to be some cable connecting the router together as well, right? Which means your router is going to be 15 meters long as well, but it'll be router to router. How many Ethernet ports do you have on your machine? Usually one. I mean, if you look at like fancy workstation, you might have 2 or 4, right? Most of the time, one. It means that if we want to connect to Google, you take the internet cable, connect to the Google, right, server, which cannot happen. But let's say you want to browse Google while listening to Spotify, you need another connection, plug the internet cable to another Spotify server. That alone is like, how do I do that? Router comes to the rescue, basically sit in the middle. It supports the ability that you can send packet to the router, and inside this packet, think of packet as a bulk of data with some information involved, saying, hey, this is the destination I want to send a packet to. These are what is about the packet, who owns it, and things like that. The router will look at that, send and kind of redirect basically. That's why it's called router. It routes the packet to the destination. All right. And in the like network setup, right? The logical structure is going to look like this. I have a bunch of router. I can go from one path to another. That if you look at this, there are actually multiple paths from the host to the destination. So if you think about it this way, this is pretty ad hoc, right? There's no particular topology to connect things. When I use the word topology, what I mean is if I draw all this connection and treating router and the host as a node in a graph, right? Are you guys familiar with the concept of like mathematical graph? Okay. Basically, it's going to be something like you have a node, right? A vertices, and you have the edge that connects the vertices, right? A linked list is a graph. A tree is a graph, right? In this case, the graph is the router and the host as the vertices and the connection as the edge. Topology means that how does the graph look, right? There are some certain topology that are kind of well known. For example, you can look at something we call a mesh topology, which is the connection would look like a mesh. We use this topology to connect a CPU core. Let's say you have 16 core CPU on your machine. We connect it using the mesh topology, right? You can also look at something that looks like a ring. I have connection between each of the nodes that goes to the left and to the right, right? This is a ring topology. Your 2 and 4 core, I think most of the 8 core CPU as well use this topology. For the network, there's also more topology. There's things like hypercube, which I will not draw because I'm not good at like more than 3D drawing. Hypercube is like you have a cube that connects like multiple cubes connecting to each other. So it's the connection is way more, way higher, right? You have things like butterfly topology, dragonfly topology, like basically just how I connect each component. All right. But if you look at this, there's no topology. I just say I want to connect to that machine and somehow a bunch of paths exist, right? And the router and the link capacity is going to be super different. Your home routers, usually these are cheap ones, right? I mean, why you need the router that can support like 5,000 machines connecting to the router? You don't need that. I mean, in your home, maybe like you have 5 desktops, I mean, for like 1 desktop, 4 laptops for all the family members. Each one, if they're rich, maybe like 5 phones for some reason. I don't know, 4 people, 5 phones. And then the TV, right? I mean, if you look at number of devices, probably less than 32, right? Should be enough. If you look at like data center, the router is going to be much more powerful, right? To handle all those things. The purpose is to send the packet from source to the destination by hopping through the network. Every time you go through the link, we said it's one hop. One hop is like one link connection. So if you want to go to the host, right, you can go 1 hop, 2 hop, 3 hops. From the top link, you can also go 1 hop, 2 hop, 3 hop, 4 hop, 5 hops through the bottom link. There are trade-offs. For example, how many people like Bangkok traffic? You can think of Bangkok traffic. All the roads are also topology. They connect destination like places, right? What would happen if I want to say, wait, how would I go to Salaya? what would be the main road? The Barom Rajachandani Road, right? What if there's a big traffic jam? Spicy, right? You can try to avoid that. It's basically this scenario. The router and the link can also have traffic jam because let's say it's a common path and everyone wants to use it. Same problem. Network has a lot of share problem with traffic control, to be honest. And the solution is also quite similar, right? There are things that done on traffic control that work on network. And also things in the network control that might be able to apply to traffic control as well, because it's the same thing. Think of cars as packets that drive from source to destination, and you have to make sure everyone can go to the destination. And if there's traffic jam, you have to reroute, right? Then the router basically forms a bridge from one network to another. Let's say you have a bunch of networking with us, like neighborhood, right? The router will connect the neighborhoods together. And the programmer view is much more simple, actually. Those are more like a logical view of the internet, how I would connect the physical devices. The programmer view, how many people heard about this thing, IP address? I think by this point, everyone in this room has used it before, right? Basically, how does it work? What does IP address look like? Like 4 pieces of information separated by dot, right? And you might have realized that the number inside the dot never go above 255, never go below 0. How many bits do I need for that? 0 to 255, that's 8 bits, right? I have 4 of that. So how many bytes is my IP address? 4 bytes, right? I have 4 pieces of information, each one is 1 byte. These IP address, there are mappings to the IP address. Some IP is mapped to what we call the domain name. Quick question, why do we need a domain name? Yeah, so that you don't have to remember the number. I mean, what if you have to remember the number for Google or Instagram for TikTok, right? Oh, sorry about Mr. Your university name. Should be mahidol.ac.th. My bad. Some of the IP address also does not map to the domain name. Sometimes they're not used, right? So you try to go to that IP, it like doesn't exist. Right? It doesn't have a destination. Communication between a process on the one host and to another host happen over what we call connection. We connect the 2 hosts together, right? A quick note, you might also heard about this thing called IPv6. Realize the date, 1996. That's before the .com crashing. That's kind of like right before the .com booming, boom, and everything crashed. Like one fun fact, check out the NASDAQ stock index. Do you know what NASDAQ is? It's basically a collection of tech companies inside this index, right? If you look at year 2000 onward, you see like it goes like this and crashed down. And then it's been recovering, and we recover from that point by now, but it took like I think 15 years to get to that point again or something like that, right? It's like, so back in the day, people think, hey, people would have much more website up, right? So there'll be a lot of hosts and server popping up. So maybe we need a lot more IP addresses. Maybe 256 to the 4 is not enough, but that's 2 to the 32. 2 to the 32 is not enough to support all the possible server and location we have to connect to the internet, right? So the Internet Engineering Task Force, IETL, say, hey, let's extend this to 128 bits. As of now, only like 32% access Google using IPv6. The majority of the traffic is still IPv4. All right. So for the purpose of this class, we will still use IPv4 because that's right now still the norm. The difference is just how you change the, like basically the IP from the v4 version to v6. so that you know the destination of the target, right? Again, think of it as the addresses, right? It's always stored in the memory in the network byte order. Network byte order has a specific meaning. It means big endian. It means big endian. What is big endian? What's endianness actually? Where is the most significant bit, right? Is it highest address or the lowest address? Okay, quick thing during the break, look it up and tell me what is big endian. The network byte order is used to, quick hint, we use that for our skill virtual memory exam. Network byte order is used in general for any integer transferred in a packet header from one machine to another. The port number is used to identify the internet connection. So you might have seen actual port, right, that allow like the chip to like dock and transfer things. Think of it that way. I mean, that's the reason why we define this word as a port. I mean, why define this thing as a port? You can establish the connection between this island and this island using the ports. And you have to designate the port that you have to go into, right? If you go into a different port, they'll be like, wait, what, right? And the structure of the internet address or the IP address is here. UINT32 is as simple as that. UINT32 means unsigned 32-bit integer. S underscore address. So that's defined. That's defined. You can use in address as the internet address. That's defined. So if you use in your program, it's known that, okay, so 32-bit unsigned integer in big endian. All right, big endian. So here's the dot decimal notation. Dot decimal notation means that I have a dot between each byte. Your IP address is 4 bytes. Dot decimal notation is like this: 202.28.162.3. Most of the time, if you're not coding and sending the packet, most of the time you use the dot decimal notation everywhere else. On Windows, on Mac OS, you just provide this IP address in a dot decimal notation. You can use the function get address info and get name info to convert between the two. Again, IP address is 4 bytes integer. Dot decimal notation is what you are familiar with as an IP address. Okay, but the computer think of IP address as 0xCA1C8203. And let's say you have the root domain. You might have realized that the top level domain name now first break into like .com, right? .io, .edu, .net, .th, which you can pick. What is that for? It's kind of giving you some hints about certain domain name. What are they? Like .edu hopefully suggests some form of university. .th maybe it's from Thailand, right? .io. What is .io? Can't be. So I kind of realized that nowadays, like one of the things that happens, like somehow you want this website as a .com, but someone took it. I just have to just do .io. So now actually the root domain span into many more names. .io is one of the common ones, and it kind of works with game. During the .com bubble, there are actually the people who try to like sign up for as many domain names as possible in the hope that someone buy the domain name, right? So, and then you have the second level domain name like MUIC, Musu. Then you can also have a third level domain name, which kind of specify the location. Like if you want to connect to any machine, you have to go through all the way to the leaf node from the root. You can go to like MUIC.io, and that's it. You go to the second level, you know the IP address. Sometimes you need a third level, like Cisco, which already died, right? Now you go down all the way down to like cisco.cs.musu.io to go to the IP address. But basically, the internet domain name can be translated. If you walk the tree, you will get the IP address. Once you have the IP address, you can use the get address info or get name info to transition between the two versions. The domain name, like skill.cs.musu.io, right? Or the IP address in the like 110.170.31.118 format, or the 4 bytes format, hexadecimal. And the domain name system, the general goal is to maintain the mapping between this number of the IP address, which I don't want to remember, to something that is an actual name, right? And if you think about it, the way I maintain domain name system is I have a huge database. I give the IP address, I get the name. All right, it's as simple as that. I have a huge table. Like if you, when I said database, think of a table with the pair IP address name. Okay. Yes. Great question. So there are multiple servers that store the DNS information. Maybe actually let's browse through that in the during the break. But yeah, basically there are certain locations that store this information, and you can browse through that. Your ISP, for example, will know like these tables because they have to know where to direct your traffic to, right? Sometimes we call it DNS server. I'm not sure if you heard about the term. So DNS server is a server, so it has an IP address, right? When you configure the router, many routers allow you to configure that. Inside the router, it's like, where is the DNS server, so that your ISP would direct to that. Whenever you type in a domain name, it will go to the server, search the domain name for the IP address, so that you can now go to destination. Cloudflare it's different. Cloudflare is like more like a company that provides service on both protecting like your like internet server that you want to expose to other user from like attacks, and also additional service that has to be on like the running of your internet server to make sure it works as intended, and try to also prevent attacks to the system. Yeah. So a quick property of DNS mapping, basically there's a program called a DIC, which also have the option plus short. Each host has a locally defined domain name. 127.0.0.1 means your own machine. From every single machine, if I type in this IP address, I talk to myself. All right. So I can do dict plus short localhost. I will get the IP address of localhost. I can also use the host name to determine the real domain name of the local host. For example, on Cisco, I can type in host name. It will say Cisco, right? We cannot try it now because it died. But you can log into one of the servers and try it out. It will give you the host name of the machine. Okay. Sample case, like we can do one-to-one mapping between domain name and the IP address, right? You can do dig plus short MUIC.io. Again, get the address. You can see the MUIC.io map to only one location, only one location. Whenever you access MUIC.io, you go to that location. Now, we can also have multiple domain names, but map to the same IP. Look at this. python.cs.musu.io and cisco.cs.musu.io go to the same location, right? Because they're actually on the same server, on a different container, right? Multiple domain name can be also mapped to multiple IP address. For example, Google Google doesn't have only one IP, they have multiple. There are actually benefit in that. Also, disadvantages, which is you have to pay the price, actual dollars to maintain that. All right. You also have to pay the price of like making sure you manage the data correctly. What happened to one machine? I mean, it should be globally seen as data Google, right? But what's going on in like .99, .103, .147, .104, .105, .106? How are you going to share the data? How are you going to make them consistent, which is like the edits is seen by everyone kind of thing, right? So that's a disadvantageous, hard to maintain, more complex to maintain. It's actually more reliable, more scalable as well, right? So you can have multiple domain name map to the IP address. Some valid domain name doesn't have an IP address, right? So I can do cs.musu.io and you get no response. So here is when you're coding, you can, again, as I said, you can use get address info and get name info to transition, and this is a graph, basically. Start from a domain name, get address info will give you the 32 bit address. With the we call that the network byte order. So with the network byte order, you can call get name info to get the domain name. If you call get address info on that, you get the IP address in the dot notation. From the dot notation, you get the name. You first get the 32 bits first. So if you have the dotted notation, you have to do get name info twice to get the domain name. All right. Any questions? So given a host name and a service name, right, get address info returns a list of sockets, address, right? Each of which will contain the IP address and the port number. So that's the IP address and the port number. Get name info function is a converse of get address info. Given a socket address structure, which is the IP address and the port number, you get what? A string, right? A string that contains the host, the service name, or any numeric equivalent if the name cannot be resolved. For example, here, what you can call, we have multiple versions of get, well, not sorry about that. Get address info, right? You can throw in the host name with the, like this service name, right? You will get the list of sockets, a list of sockets that are connecting, again, socket connecting the host together, right? And the service. And you can get the name info to get the string that give you the host and the service name. So you can also program with get address info and get name info. So basically when you have the result, right? The address info structure here at the top, right? You have the host name information in one of the fields. Then you have the socket address structure, right? So that's one socket. Then you have the list. Again, see, it's a list. Into the next, right? The next socket connection. And at the end of the day, it's a null pointer. So you can walk the list and work with it. Say, hey, is this a connection you want? This is the host name, for example. So host name at the beginning, socket 1, socket 2, socket 3. Okay. All right. Any questions so far? All right. A quick example. I want to convert the name to an IP address, right? So here, quick thing. That's the includes that we want here, just to make sure we can call the function we want to call and use the structure we want to use. These are all defined. Add some standard library, standard IO and string.h to make life easier. All right. So here you see that, yeah, okay. So I have the main code here, right? Main function. And then I have address info. This is a pointer, a list, basically a pointer list. Then I have the setting up the query part. So I have the address info as the hint, right? And inside the hint, the way I set it up is first I do memset to the address to make sure I set everything 0. So hint should be like, I want the information of this name. I first set everything to 0 to make sure if it's like some random value, I begin with everything 0. Okay. Then I say hints dot address info underscore family, set to AF INET, which is a specific constant for IPv4. When I said AF underscore INET is IPv4 format. So it knows that it's the IPv4 type format. Then address info underscore socket type, sock stream. Basically, this is a constant that tells the program to do, this is just to request the connection. Then I use the get address info here, right? With the argument input from my program as the host name. Again, the hint is telling the connection that that's IPv4, and I just want to establish the connection. Then I take the host name from the input. When I run the program, I provide the input. It can be www.google.com, right? Then if the return code is less than 0, it means that if something is wrong. Then basically print I can't get the address info, right? So now we just establish the get address info. I'll continue the code in a bit. So I'll go to the next page. Is it okay? We just now set up the query, say, hey, this is the internet address in IPv4 format. The input is in ARGV. So that's the host name we want. Now because we have the get address info call in here, right? Yes. Huh? List P is what we actually want from the return. See, I put list P here, right? This is actually the return list. We say, hey, that's a pointer. If you build the list, it points to there. So once I do the get address info, I further it return the code that say, hey, is this something wrong? If it's negative, then something is wrong. Okay. If it's not negative, I now have list P defined. Okay. I now have list P defined. So one thing I can do is, see, I have list P. I basically use a for loop to walk my list. Again, this works like a normal linked list. Okay. It's a normal linked list. Address info, remember, is a linked list have next, right? But inside the structure, we don't call it next, we call it AI underscore next. So when you go to the next node, it's P equal PAI underscore next. It's kind of defined in the structure. All right, look this up. ADDR info, it will be clear. It's a structure defined that has a pointer called AI next, which you can call to go to the next node. Okay. Then in there, right, once you have that, each item in the list, right, can be populated and read. It will contain the address info, like over here, address info, address length. Okay. And then you can use the get name info function, to put the string output that we want to do. Basically, we want to get the string output that we store in this sbuf. Sbuf is just an empty temp buffer that I want to use to print my output. Okay. I use a function called get name info to get This is the address. This is the length of my address. Give me that line. It would then basically the code print out, and then you then free the address info. Okay. The function free address info will take the list of the list of address info and free them all. Now, when you are printing this, you now get the dotted notation. Why do we need this? Because your address is not in a dotted notation, and if you want a dotted notation, get name info give that to you quickly. So just call it. You don't have to parse it yourself. Then you free the linked list after use. All right. Shall we do a 5 minutes break? I'll keep going. It's a long lecture, by the way, so it's only 5 minutes. All right. So do a quick pause here, and then we'll continue. Oops. Wrong button. That's like stop sharing. My bad. All right, let's continue. Internet connection. Basically, you connect the client and server, and they communicate through stream of bytes. I send bytes to the server. Server sends bytes of data back to me. The connection is point to point, means that they are a pair, process pair to form the connection. They are full duplex. It means that it can flow in and it can flow out, flow in and out, and it's reliable. If you stream 10 bytes, those 10 bytes have to eventually start, like basically will be at the destination. Keyword, eventually doesn't mean that it will go there directly right now, right? But eventually they will arrive. The second thing that's important, they should be in the same order. If you go byte 1, byte 2, byte 3, byte 4, destination should also get byte 1, byte 2, byte 3, and byte 4. A more advanced topic on network design, there are ways to make sure this can be fast and you can still keep the ordering. There are techniques for that. But the thing is, when I said reliable, it means that the server should see the exact same thing that the client is sending to you. That should be the minimum requirement. All right. Because otherwise the server will like, wait, I don't know how to interpret this data if it doesn't even have ordering. A socket is an endpoint of a connection, which is an IP address and a port pair. So a port is a 16-bit integer. Again, 16-bit, so it can go to like 64,000 something, 65,000 something, right? In terms of port number. There are two types of port. The first type is what we call ephemeral port. Is assigned automatically by the client's kernel when the client makes the connection request. And then there's a well-known port. Well-known port is a port that's associated with a service that is provided by the server. For example, port 80 is known for the web server. So we use port 80 when we want to connect to the web server. All right. So these are some samples of this. You can have the echo server. When you type echo, it's actually port 7. SSH server port 22. And what we see so far, when we connect to Cisco, right? Back in the day, we use port 2222, not 22. So you can change the SSH port. It's well known. It doesn't mean have to be strictly that number. All right. SMTP, which is the email servers at port 25. HTTP is the web server, which is the web service, port 80. The mapping between the well-known port and the service name is contained in that file, /etc/services on a Linux machine. So I can change the mapping. If I'm the root, I can go into the file and change the mapping, all right? What are some of the possibilities? For example, One quick thing I can do to the SSH, if I want to avoid people trying to hack into my server using port 22 because it's known SSH port, I'll assign some random unknown port. So when they try to connect, they need to know, hey, it's going to that port rather than to guess. Yes. It's like a super basic, again, like super basic brute force attack. But yes, there are multiple other ways to attack the machine, as you can see, have seen already. All right. For the connection, is basically identified by a socket address of its endpoint. So it's gonna look like that. Client address, client port, not port. I'm sorry. So it should be port, okay? And then it's a pair of sockets. So it's client, server, client port, server port. Why do we need all of this? Because otherwise we don't know where to go. Okay, we need to know the client address and the client port. Server address, server port. So in this case, the client, let's say, is address 128.2.194.242 using port 51213. The server used the port 208.216.181.15, port 80. Now the socket talk to each other is a pair, right? So the connection of socket has basically the two things combined. In this case, the host address of the client is 128.2.194.242. The server used the host address, two already. 208.216.181.15. All right. 51213 is the ephemeral port allocated by the kernel. 80 is the well-known port associated with the web server, and now you have the connection. Now you have the connection, right? The beauty of ephemeral port is when you make the connection, the client on the client side, the kernel just say, okay, that's an empty port, use that to connect to the port 80, which is a well-known web service. Okay. Here is the ugly truth question. Remember, like historically, that was like right. You can do this. Oh, like what can you do? Okay. So that's kind of like a different topic. This is basically just to establish the connection. So what we've seen so far is like, okay, how do we make the connection? Management of what we can do is done by something else, essentially. This is basically just for the two things to send bytes of data to each other. Now you can have the handler say, if I got this byte, what do we do? If I got this connection, do I refuse the connection? Yeah. All right. So the truth about your IP address is, I mean, you could think of IP address as your street address, right? What if your house is in the corner, right? I mean, in real life, you pick one, right? In the computer, well, you have three connections essentially. You have three addresses, right? In this case, I can have a client that has three IP address. Think of it this way. For example, I have two households. Household A, look at the port. No, sorry, look at the IP. Yes. So when you have the machine, right? It doesn't mean that it only have one one connection. It can have like multiple, like with even one physical device that can allow you to connect to the internet. You can have multiple like connections from different IP address. Your computer in many cases might have more than one. or can handle more than one. So in that case, it means that you have to know if I want to connect to my computer, what IP do I use, right? What would be the default? So imagine, let's say you have the household, right? In there are two devices. One of the devices is 192.168.9.49. The other one is 192.168.9.41. Is under the same network, right? And you connect to the router. The router IP address 128.9.4.55. Inside, that's a private, like internally, that's like your own network, right? So you can assign whatever IPs. The router knows, okay, .41 go to that machine, .49 go to that machine. Internally in another household, I can also have the .41 in there, right? That's the legit IP address of that computer from the point of view of your router, right? But it's two totally different machines because it's on two different networks. So in this case, the router has a different IP address. And when you connect to the internet, right? If the machine in household A dial 192.168.9.49, the first thing I do is I try to see inside my own network, is there any IP address with that IP? All right. This is a private IP address that's not visible outside. So internally you see .49 in that household, but you will not see the .49 on household B. Right? Even though it's the same IP, you are in your own network, so you only see that machine because it's a private network. In the internet connection here, you have to go through your router. The router then know, okay, go there, and it waits for the reply back from your destination. Because the destination router and the household B, for example, know that, okay, if I got a packet and I say I want to connect to the 192.168.9.41, in that case, the .41 is the private IP address, right? But if someone wants to connect to the machine, it has to use a public address, right? It has to use a public address because internally you connect to the router, you don't directly connect to the machine. Then the router can know, okay, .41 is that guy, all right? So that's kind of like the reality versus illusion. Then what is a socket, right? In the kernel, think of it as the endpoint of your communication. Basically, the socket is like basically a file descriptor. Think of it as a file, again. Think of it as a file that lets the application read and write to the network. So the file descriptor doesn't point to a file, it actually now points to the other endpoint on the other machine. Again, you have two machines connected by the socket, right? If you treat that whole thing as a file, you can then read, which is take the data out. Like when you read the file, you take the data out, or write to it, which is put the data in. The client and the server then communicate through the socket because now you have a functioning file, like whatever thing that looks like a file to the program now, so I can read and write to it, right? And now you have the server FD, server file descriptor, and the client FD, the client file descriptor. This way, I can write to the server FD. I can read from the server FD, which means I can send and receive the data. The server can do the same, read and write to the client file descriptor. All right. The main distinction between the regular file I/O, right, and the socket I/O is how the application how they open the file descriptor. So here's a quick question, right? So let's say I want to write a function pool that can take a string as an input, right? But some other time I take an int because I open a connection. I send the data over. The data can be number, string, whatever, right? How do I do that in C? How do I have a generic argument in C? Void star. What is void in C? Nothing. Void star force that nothing to be a pointer, right? Is a pointer that can point to the valid location, but the location I'm not telling what the type is yet. Now how can I read a string out of the void star? Let's say I have void star key. What if I do this? Yeah, I declare that P is a pointer, but I don't know the type. It's a generic data type. Then I cast it later. I can then do int star P as well, if I want to treat P as an integer. All right, that's how C allows generic data type. So in here, I have a function called foo that takes in the arguments. Right? In this case, I can then assign, right? If the instance of argument is a string in Python, I can do this. If the instance of the argument is like integer, I can do this. So that's Python, which is simple. In C, here's what you do. Function foo, oops, sorry. And then the kind of argument you're dealing with, for example, you pass in foo 0, assumption in this case say, okay, if kind is 0, I will cast arg to be an integer. All right. So when I use the function, I need to pair that with the type of argument I want. Can be some number. All right. So the socket address structure kind of, we want to make it generic, right? So I want to say connect to the socket. I have see here, socket file descriptor, right? And then I put in the socket address with the length because my connection can be of multiple types. The reason why we do this and not use a generic pointer void star is that when people design the socket interface back in the day, C doesn't support generic pointer yet. All right. So you might be asking the question, okay, how do we implement generic socket address? We will go into that in a bit. For casting, so instead of void star that we allow to cast with integer, pointer, and whatever, we use Stevens convention that has the socket address typed up called SA, right? And inside this struct, the first thing you see is the protocol family, the type of connection that we want to do. Then you have to address data. So socket address is going to be a 16 bytes chunk shown down there. The first 2 bytes is an unsigned number. Unsigned number 16-bit that tells the family. The rest are whatever you want to put in as a data. So in the next slide, I'll show you what if it's IPv4 connection, the internet address IPv4 format. All right. How do I do that? So in this case, you cast the socket address into another struct definition here. Look at down there. Remember the FF family from the other slide, right? Now the FF family would have AF inet. It's going to be a constant that tells the destination and the client that this is the IPv4 connection. It would read this, so it knows that this socket connects the two servers and it's using IPv4 connection. Then the next 2 bytes is the port number. The next 2 bytes you put the port number in. Then the next 4 bytes, because it's IPv4 connections, the connection made has to be, I put in the address. Now, S in address is the IP address in the network byte order. Again, it's a network byte order. Remember those 32-bit hexadecimal number. It's not 202.10.10. It's the 0x number. All right. The rest 0. The rest has to be 0. When you set it up this way, it knows, the computer will then know the socket address is now internet IPv4 connection to that port, to that IP. Network byte order, yes. It's just a constant that tells that connection is IPv4. It's the family of the socket connection type, etc. Exactly. All right. More animation bugs because there's too many things on this slide. So here's a socket life cycle. The first thing is I start the server. Forget about the red box. Sorry about that. I start the server. The server first will establish the socket will bind to the client. When you want to bind the server and the client, we build the socket from each side first. We build the information from each side. You then bind on the server side. I have to bind it to the port, and then I start to listen to whatever client wants to connect to me. Then after that, some client would begin starting itself. Say, okay, I will build a socket so I can start making connection. Now, when I want to connect, I then make the connection request, right? When I set up the socket, I know, okay, I will go through this socket from the client. The server say, okay, I will go through this socket on the server side. The server side will start to listen to all the possible connections. If the client say, okay, let's connect, then it's established the connection. All right. So after this point, the two entities, the client and the server, have connection. Okay. Now afterward, I can then read and write to the socket, because again, socket is a file descriptor. It means I can write to it from the client side. Write to it means what? Send the data over to the server. When I write to the socket on the client side, right? I send the data in from the client. Socket would deliver that to the server. Server then read the data. And let's say it's a search from some client. I want to search Google. Once I read the data, I perform the search. I go look up some possible website link that I have to show back to the client. Then I exchange the data to the client by writing the result back. Hey, here's the link that you have to show on Google Chrome client side on your machine, right? Now the client got the information, can read from the socket file descriptor to process it. And afterwards, it can go perpetually in this loop. When you're done, it's kind of like when you open a file, right? You should close the file. So you close the connection. After you close the connection, the server will get the notice from basically they keep reading what is sent from the client, right? Once you close the connection, the server would also read the fact that client is closing the connection. It's an end of file, basically. How do you know it's a closed connection? If I treat the socket as a file, right? End of file would say, okay, that's it. Now the server can then drop the client. So you close the connection. So, all right. You see how when you exchange the data, you don't do the get address info and you bind and listen again. You keep it up. You keep it up until you see the end of file, right? Because if a client wants to connect to you, just wait until the client is done before you close the connection. You don't have to redo the work in the beginning. All right. Any question from this diagram? Yes. Yes. Right. So after you connect, it has the two sockets established. And socket are file, right? So if I'm the client, I want to send something to the server, what I would do is I will write to the file. So I would write to the file from the red side of things, right? Now, when the file is written, the server say, oh, okay, something's writing to this file. I read from it. I read from a file descriptor, which is the socket. Then I process that, right? When I'm done processing, most of the time the way it works, client send the request, wait for the reply. So the server, okay, start to generate what to write to the socket to reply back. Then the client got the reply, so it reads the reply. So this is request, this is reply, essentially. But now that everything is a file, right? You write to a file to send the request over. You read the file to read the request and do the same thing for the reply. Yes. Okay. Let me rephrase your question if I understand it correctly, right? Your question is, well, if I treat this connection as a file, right? What actually physically happened? Okay. What? That's a great question, actually. The reason I want to treat it as a file is to simplify basically the way I look at it, simplify the programming processes, right? Because I have an IO, I would treat every IO using the file descriptor. So I'll treat it as if that's just another file descriptor, right? So to establish the socket, I establish the file descriptor, but it doesn't write to an actual file. What it would do is it would then establish the connection to the network interface card, which is your Ethernet card on your machine, right? And say, hey, if I write to this file, what the driver with the network driver would know is, okay, something right here, I take it. Usually the way you implement this, you have buffer. So data come in, file descriptor, even though I said it looks like a file from the programming point of view, basically what happened is you stream that data into the buffer. The network card would then know, okay, these are the connections I already established. I read from the buffer inside the memory and send the data over to the destination. Now, that's also another myriad of things that happen in the network layer, which is I have a router, I have to packet it up, right? Because I cannot, let's say I want to send 3 megabytes of image from the server back to the client, right? When you search an image, it's not possible to do it in one go, right? So what you do is you bundle parts of it up into multiple packets. The server would, the network card and the system will kind of like slice your data up, package it, ship it over to your destination. There are also the algorithm that make sure that when you listen to this incoming packet, I know how to sort them. Which packet go first, which packet go last, so you can reconstruct the image back. But from the programming point of view, if you use it as an application developers, these are files. So it's easy, right? So you say, hey, I want to write these bytes into the file. I will assume eventually someone read from it, which is the server. Now, what I will do next, I will wait for someone to write to my file, which is the server reply back. And that's it. Yeah. It's actually not allowed. It's like the way I would implement and simplify the interface, right? I want to simplify the interface so that it's easy, like it becomes the easiest I can do to program this socket essentially, right? But the way it actually gets implemented in a even lower level is okay. I mean, one thing I can do, I don't need a buffer. I can send 1 byte at a time, right? But that's kind of annoying because if I want to send like maybe 1 kilobyte at a time, I need to wait. Put it there, someone read from it. Put it there, someone read from it. So usually there's like, okay, there's a region in the memory that would store all things you want to write into this particular file descriptor. And then someone would read from it and send it over. And that's like internal management between these parts of the memory, how you would drive the network parts, and how do you send the packet over. All right. Okay, so we will quickly go over the server client example. We will not have enough time to explain everything. So what I would recommend is check out Ajahn Kanat GitHub that the link earlier, because they have the example for all the classes. You can try it out. What we are trying to do here is we want to do an echo server. Client sends something, the server got it, reply the same thing back. Okay. These are the includes that you need to do. So when you start the server, if I want to have an echo server, the first goal, I want to get a file descriptor that I use to listen to the connection. That's the first goal. All right. Here's how I would do it. The way I would analyze this code quickly, again, we don't have enough time. Oops, sorry. Here is the get address info part, which is almost the same thing as what we got earlier in the get address info example. So I listen to the incoming connection, but before I even go there, I need to open the file descriptor. So I have the port number as an input. I set up the address info. First, remember this hint thing is the address info that tell you this the connect type of connection, right? We put socket type because it's just an echo server. It's a stream socket. AI address info flags. Put in AI passive AI address config and numeric serve to set up the hints that we want to connect to the address info. I do recommend you to go to address info struct information because it will have the information on what it means to be AI passive, AI address config, and AI numeric service. All right. I need 8 minutes. So after that, we set up the address info. To get the address info, we have the port, we have the hints already. Now we get the list of ports that are connecting, right? If there's no connection, we return. So we listen to the port. Now you have the listen FC, which is the listen port. For all the list P that you have the service open up, you go through the list. Right? If there's an option that you can listen to the socket, so you use the function socket to establish the socket connection. Again, you put address info family, address info socket type, and address info protocol to establish the listen file descriptor. The listen file descriptor, the job is I want to have the socket connection that listen to the incoming bytes of data. Then you set socket so that you can start to listen, and then you bind the file descriptor to the address of the address info. Again, you get the address information, then you build the socket by saying, hey, this is going to be the file descriptor that listen to the incoming traffic. And then we set the socket option that Listen FD will be the file descriptor that we are using to listen. Then we bind listen FD with the address info that we have. Basically, now we bind the address information so that we can then start to listen. All right. Now, to clean it up, you use address info, which means you have this list P already earlier. We don't need it anymore because we already have socket open. It's done. So we free the address info. We don't need that part. We make sure that we can start to listen by calling the function listen using the listen FD. If it doesn't work, close the connection. Otherwise, you return the file descriptor. Now, listen FD becomes just another file that the server can listen to. Again, this is open up listen FD, open up the listen port through the socket connection. On the client side, almost the same way, right? Do the mem set to the hint, and then you set the socket. You then get the address info, then you get the connection. You see that this is almost the same type of code you see earlier for the server, but in this case, you have the client file descriptor, which also again you establish the socket, then you connect, right? You connect. If you connect and it's successful, right, then you clean up. This is a cleanup code. Now you return the client file descriptor. Again, the client file descriptor is just another file pointer that you can use it afterward. This is now established the connection between the server and the client. We have the connection. We haven't have the code to do something yet. All right. So what do we have to do now is on the server side, I'll keep listening. If I see something, I reply that thing back. Okay. If I see something, I reply that thing back. So the main code is I then first accept the connection through the listen FD. Then when I want to listen, right? When I want to listen, the first thing maybe I want to say connection from, right? Connection from to get the host name information. I can do get name info to get the host name information, which I can print host name with the port. So once that's done, right? This is what we run. There'll be a function called echo logic, which is basically take the connection and listen to something, echo back, listen to something, echo back. All right. This main code right now is just to set up like, hey, we have the connection from this host through this port. All right. Now we can then read from the echo logic. So the code for echo logic is here. Basically, I have connection, which is file descriptor, right? The key here is everything here looks like a file. I use the function read. It's UNIX.io. Remember UNIX.io from the other lecture on Tuesday. I read connection FD, read the content in the buffer with buff size. So I can configure buff size to be any number. I read these many bytes from the file descriptor. Once I read it, if it's greater than 0, it means I'm reading something. All right. If it's greater than 0, it means I'm reading something. It means that I start to read something from the client. I then start to gather the input, right? Because we use UNIX.io, you don't have scan F and read the whole thing. You have to read a chunk at a time. So you have this pointer and have the right buffer that these are what I'm reading. This is what I'm reading so far. All right, these are what I'm reading so far. until it's at the end, so I can echo the whole thing back. Okay. Now, once I'm done, I'm using the function write again through the same connection FD, right? I write it back because we are echoing. Basically, we write it back to the client. Okay. So that's it from the server side. From the client side, it's kind of like the same. You start to establish the connection. You also have to close the connection. Once you have that, right? Once you have that, you first write to the server using the client FD, which is the socket established already on the client side. So you write that. And once you're done, you read at the end. And that's it. Afterward, you close the connection and you're done. So that part is the loop body that performs the write loop into the server. Once you're done, you read it back. So that's just echo. We have in-class exercise on the canvas. So please try that. It's due next week. First, I would definitely recommend you to clone the repo and try this yourself. All right, try this yourself on your machine so that you can establish the server and the client. Okay. That's it for today's lecture. We just about right on time. Sorry about the rush toward the end. It's a little bit longer than I expected. We'll see you guys. Well, exam will be released midnight today, like 12:01 Friday. You have 48 hours for that. Good luck all. I'll be here tomorrow from 9 to 1 o'clock. 9 to 11 in 1402. 11 to 1 here to answer any question, also available on Discord. All right, I'll be online there as well.